Good afternoon, everyone, and welcome to the Distinguished Fellow Colloquium by Professor Sriraam Natarajan. As you all guessed, Sriraam is Distinguished Fellow of the Robert Bosch Center for Data Science and AI, and he has been a very valued collaborator and a long-standing collaborator with the center. And so we are very honored and thrilled that Sriraam chooses to associate with us in over time, right? I think Sriraam and I go way back. We started when talking to each other back in 2005, and after a lot of false starts, then we actually started doing research together. And we have been working together for more than a decade now, and been multiple jointly advised students and so on and so forth. So I'm really thrilled to have him back here. And so some of you were attending his workshop for the last 2 days, but today we're going to have the colloquium style talk. And so since Sriraam agreed to be a distinguished faculty fellow for the center, COVID struck, and we never could properly acknowledge that till now. So as a token of from our side, I'd like to present it with him with this plaque. Yes. Over to you, Sriraam. Thank you.
Yeah, no, I think it's okay. All right, so thank you so much. It's actually my pleasure to be associated with the center and seeing its growth in the last 5 years. It's been phenomenal. I'm looking forward for more, and as I said during the workshop, we are also looking to jointly advise students and stuff. So to build a bridge between IIT and UT Dallas. That's our hope at some point. So thank you for this, and thank you everyone for attending here and virtually. Appreciate this. So I'm going to talk about our more recent work on human allied learning of symbolic deep models. For those of you who have watched the machine learning Twitterverse, there's a lot of argument going on between the symbolic world, headed by, say, Gary Marcus, and the deep world that's headed by Jan LeCun. But deep down, everybody knows that you need the combination for things to work. And so if you go back to the famous economist Daniel Kahneman's, the two-level systems, I think that's how we humans operate, and we tend to think of abstract thoughts, but then when you're executing, your muscle memory just does things, right? So as a classic example, if I'm planning, say, to come to IIT from my parents' house, who live a little bit about 3 to 5 kilometers just beyond Velachery, and I'm driving here, I just plan in terms of what time should I go, what should I take. I don't really plan on how much I should turn my throttle, how I should brake, and so on. That's just done by my neural stuff. It's instinctive. Whereas everything else, how to plan this lecture, how to give this lecture, it's much more deliberative. And as somebody who has been working on this for a while now, I feel like the combination of deliberative, slow symbolic reasoning with fast, accurate reactive reasoning that neural networks bring in, I think that's where the power is. So what I'm going to do is really tease you on some of these. But remember, this is a high-level colloquium talk, so I'm not going to drill down on details. But if you're really interested, feel free to reach out to me. Of course, also interrupt me or ask questions as we go. So before any talk, of course, we have to thank all the collaborators, because without them, it's not possible. So I've listed all my collaborators, my advisors, of course, Professor Ravindran Balaraman from here, but also my fabulous team. We call ourselves the Starling team, Statistical Relational Learning team at UT Dallas. And this is work of, the work I'm going to talk here is from some alumni, Devendra, Mayuk, Navdeep, and Nandini, and from some current students, Harsha and Suvan. And of course, it's sprinkled the work of all the others. So we have about 9 PhD students who have graduated and about 6 to 7 who are currently with us. So it's a good team. So just before I start, I gave the same example in the workshop as well. When I'm saying symbolic, what do I mean? I mean things that we can interpret, we can understand, we associate symbols to, we associate some semantic meaning to. So as an example, let's say I'm interested in predicting who's going to have a heart attack, right? So let me just do this for a second so I can. So I'm interested in predicting if a person is going to have a heart attack. Okay, so I'm predicting heart attack of a person. Then the first thing I check is if the person is male, the gender of the person. Okay, and then we can start drilling down. We can look at the cholesterol level of the person. So we can cut the person's age at 40 and say, is the cholesterol level when the person is over 40, has it been ever greater than 200? Okay, so if there are any people who are here over 40 years old, don't worry, these numbers are made up. Okay, so don't get a heart attack just looking at these numbers. So the cholesterol level of a person we are checking, has it ever been greater than 200 when the age is greater than 40? So this in logic, you use what is called as an existential quantification. So you're basically saying, if I look at this record of this person, does there exist a single measurement that is greater than 200 when the age is greater than 40? Okay, then the probability of a heart attack is 0.8. Remember, I'm looking at predicting whether somebody is going to have a heart attack, right? So these numbers don't add up to 1, whereas this is 0.8, means the probability of not having a heart attack is 0.2. Okay, so that's where you should do your normalization, not across the leaves of the tree. Okay, each leaf has its own normalizing. And then I'm maybe the person is either less than 40 or has never had a cholesterol that's greater than 200. So those are the two conditions, because what happens here is it's looking at age greater than 40 and level greater than 200. So it's a conjunction. If you take a negation of a conjunction, you get disjunction of negations. So it could be because the person is less than 40 or the level has never been greater than 200. And you come down, now you look for the father of the person and you say, does the father of the person have diabetes? And let's say the answer is yes. Again, you come down, left is yes in true, the test is satisfied, right means the test is not satisfied. Okay, then you look at the BMI of the person at the age of 55 and see if it is greater than 50. So the thing I want you to note here is, I am talking about attributes of this person, I'm talking about a relation, my dad's attributes, and then I'm talking about specific grounding, specific value of some of these attributes. So this is the power that you can get from relational models. You can get these abstractions at the level of objects, at the level of ground instances or subpopulations. So you can talk about things like, are these students of all these student population. We can talk about a friend of a friend of a friend. Okay, you can talk about in general, you can talk about specific values, which what you would get from a classic machine learning model, like a feature value, or you can talk about groups of features at a higher level. So that's the power of these symbolic thinking. Okay, another example, and this is a very powerful example due to Pedro Domingos and his group on Markov logic network. So here, for instance, the first one says smoke implies cancer, or in some simple words, smoke causes cancer. Okay, and the or if you smoke, you get cancer. That's really what it means. The second one says friends have similar smoking habits. So if X and Y are friends, then if X smokes, Y smokes, and vice versa. Okay, but remember, these are not rules that are always true, because these are true rules that are that we know as knowledge, but there is always some noise, there is always some uncertainty associated with these rules. So what do? We soften these hard rules by adding some weights to it. So the notion of these weights is that you can convert them as probabilities at any point. You just take some sigmoid function, you can get some probabilities out of these. So that's easy to do. So these are real numbers. So you can think of this as 1.5 is the weight given to this rule that smoke causes cancer. And friends have similar smoking habits. I'm one of the biggest passive smoker in the world, because 3 of my best friends, at least 2 of them, used to smoke a lot. One of them just gave up. Okay, and so I mean, it's not that we really smoke. I mean, he smokes, I don't. But the rule says that friends have similar smoking habits. Now, smoke causes cancer has a weight of 1.5, while the second rule has weight of 1.1. All this means is that the first rule is probably more true in the world than the second rule. That is, it is satisfied more often in the world than the second rule. Okay, and how does it exactly satisfy? That you have to take the log odds. So the ratio of how much they satisfy is log of 1.5 divided by 1.1. You do the math, you'll just get it very easily. Okay, don't worry about the math. So what I wanted to say was that when I talk of symbolic methods, I talk of these types of rules, because you can see I'm talking about an attribute of a person, whether somebody smokes. I'm talking about relations, friends, and then we can talk about friends of friends, and so on and so forth. You can look at the social network. You can basically say, instead of predicting this, if I want to say if a researcher is popular, then maybe in the machine learning literature, you could say things like, well, has this person published with somebody who's published with, I don't know, Tom Michel or UD Apol or Jan LeCun, then maybe, at one hop, you're famous. All right. So the point is that you can write rules like these in logic. Of course, learning them is harder, but there are many solutions exist, and I'm going to present some of these rules as we go. Okay. So what I'm going to do is remember this. If you look at anything like this, there are two components to this. One is the rule base. So you're going to learn a rule, and the second is the weight or probabilities that you can get from it. So this is your statistical part. This is your symbolic part. On the left is the statistical part. On the right is the symbolic part. So the question is, how can we learn such models? So what I'm going to do is really organize this talk into kind of a lesson learned, because this is really what we have learned over the last 10 years when we have worked with problems like this. So the first step is obviously, what if I learn the rules and then I learn the probabilities on top of it? Okay, I'm going to talk about that actually second. Before that, what if we learn both the rules and the weights simultaneously? Okay, so that's where we're going to start. So to do that, I can, again, if you are in my workshop, this is just a refresher, this slide. I'm inspired by this idea of letting 1,000 flowers bloom. So why have one monolithic model when you can learn many weak predictors? Okay, so think of, again, predicting who's at high risk of COVID, okay, or high risk of severe COVID, right, where you have to be hospitalized. Well, the answer is not one feature. Okay, initially they said, oh, if you're over the age of 70, but it's not that not all 70 years old who got COVID ended up in hospital. Then they said diabetes, again, not all, right? So the point is that there are a bunch of weak signals that together amplifies the probability of getting severe COVID. Okay, and so we were kind of like inspired. This is, of course, way before COVID. We were inspired by this thought: why build a logical model that is very monolithic, like very strong weights with rules? Why can't we allow for some weak weights and a lot of rules? So instead of learning 10 rules with very high weights, what if I learn 100 rules with very small number of weights? And so that's the idea of gradient boosting. Many of you should know XGBoost, right? I mean, right now everybody should know XGBoost if you do something with machine learning, right? And so XGBoost is actually an instantiation of gradient boosting that Jerome Friedman developed in, I think it's in 2000. I may be off by a year, but I think it's in 2000 or 2001. The idea is very simple. I start with an initial model, and the initial model could be an uniform distribution, could be a domain knowledge that an expert would give. And then I take my data and I make predictions on this data using the current model, what I have. Okay, and the difference between the data and the predictions becomes the gradient. Let's say we are predicting who's going to have diabetes. Okay, you're Nishant, right? So Nishant is very young, he seems fit, he doesn't have diabetes. Okay, I'm on the other hand slightly older and I do have diabetes, so I have diabetes. So according to the data, Nishant doesn't have diabetes and I have diabetes. Okay, and I'm trying to predict who's going to have diabetes. So the model initially says Nishant is going to have a diabetes of say 0.4, and Sriraam is going to have diabetes of 0.6. Okay, probability. Because he doesn't have diabetes, the actual number should have been a 0, but it's predicting 0.4. So his gradient is 0 minus 0.4, negative 0.4. I have diabetes, so it should have been 1, the probability. My model says 0.6. So 1 minus 0.6 minus positive 0.4. So he's negative 0.4, I am positive 0.4. In machine learning terms, I'm a positive example for diabetes. It's not positive in the societal terms, but positive for diabetes prediction. I'm a positive example, my weight is greater than or equal to 0. He's a negative example, his weight is less than or equal to 0. So what does the model do? Push all positive examples towards 1. and all negative examples towards 0. So what I do is, in the next iteration, we are not learning to predict 0 and 1. Instead, we are predicting minus 0.4 and plus 0.4. So that is the small model that I'm going to add. So in the third iteration, it could be now predicting that he has diabetes with 0.3, and for me it could be 0.75. So his gradient is negative 0.3, for me it's plus 0.25, and we keep doing this repeatedly. So what we are doing is, we are taking small steps in this gradient space to go to the final model. Okay, of course this is not all black magic, it's kind of grounded in very simple math. So let's say you're taking the probability of predicting if somebody is going to have diabetes, or just in this case probability of predicting let's say xi is true. In a graphical model sense, it's called the parent of xi, but in the general case, think of these as features. Given the features is it's just a sigmoid. Okay, e raised to psi divided by 1 plus e raised to psi. What do we do in classic machine learning? You write out the log likelihood essentially as the log sum of the log probabilities. You add your fancy regularizer, whatever you want to, and then you take gradient with respect to these model parameters or thetas. Okay, but in the functional gradient boosting, the change is that instead of taking the gradients with respect to thetas, you take the gradient with respect to size, the functions. So once you start taking the gradient with respect to function, and this is where the clever work of Jerome Friedman, which is over 20 years old now, comes, is that you can when you do that gradient, it has this nice formulation, which is the probability. This is the probability of being true according to the model. This is whether it's true according to the data. So you're explicitly trading off what my model says with what my data says, and making sure that the model comes close to the data as much as possible. Okay, and you do this in some sense iteratively. The key insight is that you drop this summation, which is what we do when we do over all the data. So what do we do in gradient descent? You take a sum over all the examples, go back, take a step, and then do the sum again. Here, instead of doing these sums, you take point-wise gradients. That is to say, instead of computing the gradient over all the examples, do for each example separately, and address each example separately, and create a new training set, and keep going. You know, funnily enough, for people who have done this for a long time, if you have a nice vectorized data set, so a nice IID assumption, nice beautiful vector data set, XGBoost more often than not beats deep learning, hands down. It's order of magnitude faster and works like a miracle on many of these problems. So if you have, let's say, a non-image data, I would say try XGBoost before you even think of developing a deep architecture and spending time on it. Okay, and what we have done is, we have taken this, and you see these trees. These trees are the symbolic trees that I presented in my first slide. So all I did was basically looked at this and said, why not just replace these trees with some logical rules? Then I get the power of both. I can do my logic, symbolic reasoning, but I also get the power of gradient boosting, the statistical learning, and then combine both of them together. And of course, we did this for Markov logic network. I just want to highlight one result. Okay, we did this on predicting who is advised by whom, and you can see this RPT means it's learning a single tree, and you can see that boosting was order of magnitude more effective. Okay, but less efficient obviously, because if I learn a single tree, it's going to be much faster than learning 20 trees. But the thing is, what I don't have here is the state of the art Markov logic rule learning was about 36,000 times slower for a fraction of the performance. So it's there in the paper, of course you can see it, and we did this in the context of cyclic graphical models. I'm going to again skip this for brevity. We have done this on all these standard benchmark data sets, predicting the movie recommendations, predicting who cites whom, discovering new relations from, let's say, a movie database. One of the interesting work was also learning to play games and figuring it out, and also we did some NLP before deep learning took over. But that's not really what I was proud of. I'm really proud of what the real applications of these are. Okay, and we've also done this in the context of logistic regression and boosting logistic regression. I'm flashing the slides here on purpose. I don't want to spend too much time on this. So if you want to ask questions, I'm happy to explain this. But relational logistic regression has one power over Markov logic networks, in that you see when I'm doing when I'm doing these relational data, right? think of predicting friends, right? I'm just going to quickly throw around, and I'm looking at the younger population. Who has about 1,000 friends in Facebook? Is Facebook the latest? Still the social media, right? Instagram. Okay. Who has 1,000 friends in Instagram? Followers, I guess. 1,000, 10,000. You see, Instagram followers is still one way, whereas Facebook is two way, and I like the two way connection. So we'll still stick with Facebook. Anybody has 1,000 friends? Great. Do you think you're popular? No, you are compared to me. I have half of yours. So you are popular. But what is the population of India? 1.2? Okay. So how many friends relations are possible just in India? 1.2 square, 1.44. Right? Now the question is, how is 100,000 compared to that number? Because in most real life, most people are not friends. Okay? Most people are not married to each other. Most people don't even love each other. Most people don't even like each other. That's what a real data is. When I get my real data, 99% of my data is all negative examples. 1% is positive examples. You have to be very careful when we work with such data sets. It's a huge skew and imbalance. And what we came up with was a method that actually allows for that skew. That's the only message I want to give you here. If you change the scale, suddenly go, analyze a social network from a smaller country, say Maldives, and then I come to India, you want your method to scale reasonably well. Relational logistic regression can do that. And it comes with some side bells and whistles. I'm not going into the detail, but we can boost it. And again, we got some great results compared to the baselines. Okay. And of course, many of you should know what a restricted Boltzmann machine is, right? Because anybody who has done something with deep learning, this is the first so-called deep learning model that people work with, right? Where you have a, I'm just going to move this so we can see this. You have some output nodes, you have your input layer nodes, and then you have these, visible connections, and essentially it just performs sigmoid functions and then propagates it, and then you get the results nicely. So what we have done is we figured out a very principled way of even boosting these by gradient, functional gradient descent. So what you might be asking, what is the advantage? You see, the advantage is that you have only one layer of hidden node here, which means the expressivity of your RBM is pretty small. But if you boost it, you actually get slightly greater expressivity. So instead of building a new architecture altogether, I'm just boosting a set of smaller RBMs, and we got some phenomenal results on this as well. Okay. So once I get back to this, oops, sorry. So yeah, I mean, compared to, but again, right, compared to the original gradient boosting, the results were not that impressive. But compared to training a vanilla RBM, it was way more impressive. Okay, that's the story I wanted to say here. And so now let's go to the next one that I wanted to talk. I don't know why my clicker is doing this, but let's talk about the other way, where I'm going to learn the symbolic model first, and then augment a deep model on top. Okay, so the way we do it, we did the same thing with relational restriction Boltzmann machines, where we said, okay, now we can take a schema that you have, any schema, right, that talks about students and professors, and then what we did was we generated some sort of a graph representation. So think of it as a graph. So students have professors, and then they take courses. Professors advise students, professors teach courses, students register for courses, but they also TA for courses, and both of them publish together. So you have a graph of students, professors, courses, papers, and then adjust between them. So all we did was we started doing random walks on this graph. So you start from a student, let's say a positive example says Nishant is advised by Ravindran. So we start from Nishant and find some paths to Ravindran, and then we kind of write a rule for that, basically connecting the path. And we do this multiple times by choosing multiple examples. So you create multiple sets of these rules, and then make these rules create a feature vector representation of these rules. Okay, so you can ask, because remember, Nishant might have 5 papers with Ravindran. I might have like 20 papers with Ravindran. So he's going to have, if we just put the same vector for both of us, it's incorrect. So we can do one way or the other. We can ask how many papers has he done and give that as a count. So that is this one. okay? Or to construct the feature, you just make it a Boolean. Is there a single path that exists or not? And if it's so, you make it as a ones and zeros. And you know, in logic, this is called existential. You just say if there exists a path, and this is in some sense not universal, but it's counting on top of it, okay? And then you use that and put that in your RBM, and of course we use the La Rochelle's discriminative RBM here and trained at RBM, and we got some really very good results compared to say standard vanilla Markov logic network type learning. RRBM C and E, the count and existential did very well. But the cool thing for me was how very powerful just this Boolean representation was. Is there a path was more important than saying how many paths exist, and that's extremely important, because again this is coming because of the fact that we learn a lot of these rules. If you learn a lot of these rules, they can be very flexible and you can be faster. One of the powers of deep learning is because of the depth of the architecture. Same thing translates to these as well. We also did the same idea, but this time built a neural network. So we started with things like, you know, kind of looking at a graph. Let's say a person directs a movie, person could act in a movie, and movie could be in a single genre, and then two genres can be the same or not, or you can have inverse relationships that talks about two people being same or not, and then inverse relationships that says is a movie where a person has acted in. So you can have these different relations in a graph, and then what we did was we started walking these graphs and created some random walks, but the random walks now started where in the hidden layer. So you have the output layer is just these edges and nodes in the graph. You just put that as your edges and nodes, and then in the hidden layer you simply put the random walks and connect the random walks to the output layer, sorry, to the input layer. Whatever you know nodes appear in the random walk, connect them to the appropriate hidden layer. Hidden layers are random walks. All the nodes are in the output layer, sorry, in the input layer. Connect the input layer to the hidden layer if the input node is present in the corresponding random walk. Okay, that's a simple construction. And then we had an extra layer where it was called the combination rules. Again, because again Nishant could have 5 papers, I could have 20 papers. And to make sure that we are both done properly, we have to aggregate that. So we take an average of the number of papers or count depending on what you are looking at. And again, constructing that, we were doing very, very well compared to simple vanilla learning of rules and then weights. More recently, our phenomenal student Devendra is working on these local graphical models called as actually no, this is the GCN work. So we did the same thing, except instead of using this in any neural network, we use a GCN. Okay, and a similar idea for a graph graph neural network, and essentially got phenomenal results. This is the one I wanted to talk about, where we were learning a bunch of these rules, but in the context of a local model called as Geifman models. Okay, Geifman's locality theorem basically says that neighborhood information is sometimes all you need in a graph. So if you are in a big graph, all I need is this neighborhood information to make good predictions about something. So if I'm saying whether you're popular or whether whether a person would be advised by a student, then maybe just the local information of the student and the advisor are all you need. So what Devendra did was basically figured out how to construct this local information using, again, random walk type stuff. Okay, purposely keeping the details down, but just giving you the flavor of what these things can do. And I'm leaving the details aside, excellent results on some of these real challenging problems, particularly the Neverending language learner by Tom Michel, which crawls the web and constructs this gigantic repository of knowledge. We were able to look at the sports domain in that, and we got some excellent results. Okay, so I'm going to kind of like pause here to maybe talk about what were the lessons that we learned, right? So sequentially, where we learned the random walk and then put the deep model on top of it, had some very good desirable properties, in that this deep statistical models were able to capture these correlations very well, whereas simple models and log linear models and stuff they did not capture this kind of information. But the thing is that the logic itself was not very well connected to the deep model. It was like, yeah, there is this rule, yeah, there is the count, I'm going to put them together, rather than saying there is an organic relationship between the two of them, which the learning together on the right side, it was able to get, because there we are looking at the gradient boosting type stuff, where when I'm learning a tree, I also learn the leaf weights with it together. So and they pretty they were pretty good, but again, if you learn very large trees, you can easily overfit. So you have to be careful on how you control the depth of these. And one of the things that I did not get to talk about was, if your data has a lot of hidden features, these boosting methods are phenomenal. They still work very well. You don't need any EM, you don't need any imputation technique. You can just run this and still it works very well. Again, because of the fact that, let's say if A influences B and B influences C, boosting basically ignores B, because B is hidden for a long time. It puts a weak link between A and C and amplifies that signal, and that works very well. So that's one of the reasons I always prefer gradient boosting, and that's the first thing that I ask my students to try. In 2010 or 9, I would have told, try an SVM with this kernel. Okay, in 22, my suggestion is always try gradient boosting and then go for deep networks if you have to. So I'm going to take the last 15 minutes, 20 minutes, or maybe just 15 minutes to talk a little bit about my passion in this whole thing. Is that human is not a mere labeler. Okay, humans, particularly the humans that we work with, they are domain experts. They are physicians who have 40 years of experience on the field. I work with many of these people have been MDs for about 40 years now. So they have a lot of knowledge that they have collected, and they have gathered a lot of information. Secondly, if you look at the field of medicine itself, or astronomy, or anything, we have had centuries of centuries of knowledge. Why are we ignoring this knowledge when we just take something and put it in, let's say, a deep learning algorithm? You can't just say, oh, just train a new architecture. That's not the solution. You want to be able to take the human knowledge and use the human knowledge along with the data to learn a better model. Okay, so that's really the grand vision for us. Is the machine agent. Machine is like a student, human is like a teacher, and the student should be asking the teacher all these questions. I have a 6-year-old, okay, and every now and then he does this. He comes to me and he says, shh, I will ask you questions, you keep quiet. So if he's doing some Lego and I try to put, hey, you shouldn't be doing this, he immediately says, shh, you keep quiet, I'll ask you when I want to. You see, that's the ideal student-teacher interaction, because I don't know what his mental model is, right? Same thing, when a machine learning agent learns, it's not very transparent to the human. So if the system can figure out, here is my region of uncertainty, here is the set of data points for which my model is clearly failing, and here is what they share in common, can you tell me something about them? A classic example, I'm seeing, let's say, data sitting on top of a building, in a college town, I don't know, eating a donut and coffee, and I'm seeing a bunch of cars go. 50% of them stop in stop signs. I was in a signal yesterday by this Velasquez junction trying to turn left. I was waiting because it was red, and people were going around me. And these were like big buses, just turn left and went, it was still red. So I'm looking at this, and let's say I'm an agent. I really wish I was an AI agent. And I'm just looking at this and I'm saying, what is going on? So you ask the human, what is going on? What should I do? And the human could say, well, if that is a signal, I prefer that you wait if it is safe to do so. Clearly what I did yesterday was probably not very safe, because the bus was coming right behind me. Maybe I should have moved, right? But the human can give you that advice and say, I prefer you wait if it is safe to do so. And the system should be able to use that example and then kind of make its own informed decisions the next time. And so that's what the idea is. There is an expert, okay, the system is executing some actions, generates some explanations, and then asks the question, elicits the question from the human expert. And we want to be able to do this in the context of neural networks, in the context of probabilistic graphical models, reinforcement learning, probabilistic planning, and we do it with all these different topics. Okay, so that's our research. And because again, right, knowledge-based machine learning, I love this quote, right? If you have this Tom Mitchell's book, I think it's 1.3, you should read this. Bias-free learning is futile. The futility of bias-free learning. If you have two competing hypotheses, they may have the same exact performance on your data. If you don't have a good inductive bias, the bias, unlike in the social world, in the machine learning world, has actually a good meaning. If you have an inductive bias, which is a bias that you can provide to the learning system, so it actually, differentiates between two competing hypotheses, that bias is extremely valuable. Okay, again, this is not a new idea, and that's what I want to make very, very clear. I'm not talking about giving advice to the machines as if I'm the first guy to do it. John McCarthy in 1965 wrote this wonderful paper on advice taking systems, and then Jude Shavlik and his group did a lot of work in 1990s on this area. I'm just following that legacy and trying to figure out what to give as advice. And then the question is, what is an advice? Advice could be what is called as a qualitative constraint. As BMI increases, the risk of heart attack increases. As the blood sugar level, called A1C, increases, the risk of heart attack increases. This is called monotonicity, monotonic information that talks about how the effect of one variable is on another variable. One feature is on your class value. You can also put together synergistic stuff. You can say higher BMI has a higher risk of heart attack with high A1C than with low A1C. Okay, now what you're talking about is two features interacting together when causing something as a third feature, or heart attack in this case. The other type of advice is the precision recall trade-off. When you are designing system, this is something you should think about. Okay, and I gave this example again yesterday. I'm giving it again today just to make sure you get it. If you are developing a system for disease prediction, you want to maximize recall, because what you want to do is you don't want any false negatives if you're building a disease prediction. So think about it. If I predict somebody who has COVID as not having COVID, then I'm creating a mini cluster there. So not all mistakes are equal. What happens if I predict somebody who doesn't have COVID as somebody has that they have COVID? Yeah, there's a bunch of mental stress, yes, and then maybe you clear them the next day. But the other side can actually lead to a small cluster. COVID is okay, but if you think of other things like measles or more risky things like Ebola, even one false negative can create a huge cluster. So we have to be very careful when we tune our algorithms. They have to be trustworthy and they have to be safe. On the other side is LinkedIn. I made this joke yesterday. Today morning I got the email. Indiana University is looking for a postdoc position. No, what does it say? Positions that you may be interested in. Indiana University is looking for a postdoctoral fellow in Precision Health Initiative. And all I can do is this, because I am the PA of that grant. And I've done my time. I was a postdoc 10 years back, 11 years back. 12 years back, sorry, 12 years back. So why? Because they are maximizing recall when they should be getting precision right. And this is ridiculous. If this happens few times, I'm just going to unsubscribe from LinkedIn. But that's not as bad as the other problem. So, but as machine learning practitioners, when you go out there, think about this. Think about, do I want to maximize recall or precision? Turns out this can be elicited very nicely from the domain expert. Third one is, of course, preference. I just gave you an example of whether or not you should turn left at a signal when the signal is red. Okay, and again, preferences are very powerful and they can be given. There is another one which I really like, is this idea of privileged information due to Wapnick. So again, this is a real study, real example that we have. So we were predicting Alzheimer's. So we have the electronic health record, we have these MRI images, and in the clinical study that we were looking at, just in that clinical study population, we also had cognitive tests, periodic cognitive tests on these Alzheimer's patients, and they were given all these smart watches and they were put in smart homes. So we had a lot of sensor data. But if I build a model using this sensor data and cognitive tests and use those features, they are not available to the doctor when the doctor is making a diagnosis in the clinic. In the clinic, the doctor has access to only the EHR and the images. So what these two should do, the sensor data and these cognitive tests, is that they should allow the doctor to get to a better hypothesis. In multiple competing hypotheses, they serve as constraints. You can even think of them as regularization that is there during learning, but not during deployment. So what we did was we looked at many of these advice and as a constraint, as basically providing constraints to the objective function. Remember the I minus p I told you for gradient boosting. So all we now do is take this I minus p and then have another term which is essentially a regularizer that looks at the number of advice constraints that are satisfied and the advice constraints that are violated, and they basically give us whether one model is superior over the other. Okay, and again, I'm not going into the detail. We have done this in the context of probabilistic graphical models, doing causal learning, boosting. We did this for fast counting as well, but now we have started doing this on sequential decision making, reinforcement learning, inverse reinforcement learning, planning and imitation learning, and so on. One of the work that I want to highlight quickly is this end-to-end decision making that we have just started working with. So there is a, Minecraft, most of you now know Minecraft, right? So we're working with this Minecraft domain, and there is an architect which is the agent, and then there is architect who tells what we need, and there is a builder which is the agent which builds the towers, the whatever we want to build. And so the architect can say something like, build a tower of 4 red blocks. It's said in natural language, English. And then there is an NLP engine that converts it into a formal representation, and a planner that learns how to construct that. But during this time, it is trying to learn what a tower means. And then I can say, add a row of size 2 to the right. So it builds this tower, and then I'm adding a row of size 2. Now I'm going to call it an L shape. And then once you have this, and we write it as ELL because L had some issues, so we had to call it ELL, which is essentially L. Now I can say put 2 L shapes to form a rectangle. Now put 6 rectangles to get a cuboid, and so on and so forth. So what we are doing is, by basically like how I teach my kid, we work with this system to teach concepts from lower level to higher level. But the thing is that the system is learning, and that's where I'm very impressed, because the question it asks are extremely interesting, because it can ask, after constructing one example and learning a concept, it says saying, should the width of this new shape be same as the height of the tower? Answer is no, because it turns out that in one example the L was exactly symmetrical, but that's not always the case. Then you can ask things like, height of the tower is 1 more than the width of the shape, should the height be 1 more than the row? So it is trying to generalize. It understands that this is one example, but maybe this example is just too specific. I need to be very careful when I am learning what the L shape means. So what we have done is figured out a way to generalize from a very small number of examples by asking a small number of questions. The other way to think about it is that we feel that human advice is kind of a complement to data, and that's what you're seeing here. Okay, and I just want to finish off with this really exciting work with Professor Ravindran, and where we are again, remember the 2-level systems that I talked about, we exactly did that. So again, right, if I'm planning to let's say go to O'Hare, give a talk at where is this, University of Illinois Chicago. Okay, so let's say I'm going to UIC from Dallas, then again I'm going to plan it at a high level. Take my flight, get to the airport, take the flight, get to the Chicago, take a cab, go there, or rent a car, drive. My brain doesn't tell me turn 30 degrees right, press the accelerator with so much force, and so on and so forth. That's done at the lower level. So what we did was, we had a planner, probabilistic planner, a symbolic planner at a high level, which decomposes tasks at a fairly high level, and a lower level reinforcement learning, that is a deep reinforcement learning, that learns how to execute from lower level percepts. As an example, again, right, let's say you're thinking of a taxi domain where you're picking a passenger and dropping the passenger off in a destination. Then you're basically saying, I want to transport both P1 and P2. To do that, I have to transport P1 and then transport P2. To transport P1, I pick up the P1 and drop P1. So this is my planner at a high level that just decomposes my knowledge, symbolic knowledge. And then how it exactly picks up and drops off is left to a RL agent. So this is deliberative, it's slow, it's deliberative, it understands this slowly, it's a reasoning engine. At lower level, it's a very fast reactive reinforcement. Okay, and it works. And what we have done is actually define what this does is, look, if I learn how to transport P1, I can actually very easily learn how to transport P2. So I can transfer faster, I can generalize faster. But most importantly, I can also make sure that if I don't have this hierarchy, this reinforcement learning problem is going to be huge. So I'm going to define smaller reinforcement learning problems, because at the lowest level, the RL is faster. So the reinforcement learning problem is not considering the whole thing, it is only considering going to that place and picking up. Make sense? So what we've done is decompose a high level problem into smaller problems that can be solved efficiently. And so if you look at the results, of course, we're beating the heck out of everything. This was published 2 years back in ICAPS. And the most important thing is that if you learn to do, if you transport a person, right, you can transport any number of people. There is no learning once you learn for transporting one person. So that's the beauty of this method. And we have, of course, combined it with deep RL as well at the lowest level. So now instead of using this as a grid, we can basically use this as an image. And the lowest level RL agent figures out how to operate in the image. Higher level planner will decompose the problem. And there are 3 papers that are under review where we have got some excellent results as well. So I'm going to conclude the talk by saying that we need to really understand the combination of high level learning and low level learning, the combination of logic and deep networks. Initial directions seem very interesting, but one thing that I'm not very happy is that still everything is kind of empirical. I have one slide with lessons learned, but I really want that lessons learned slide to be more theoretically sound, and I think there is a lot of work left there. And of course, the way I see it, with all due respect to adversarial learning, most people are still allies. Most people still don't want to break systems and so on. So we want to be able to build systems that treat human as an ally and work with the human in learning the better model. And of course, there is a lot of work left in terms of deployment. I am personally very interested in doing this for healthcare, because that's one area where I think AI and specifically data analysis can have a huge positive impact in society. And so I'm very particular about it, but of course we can do this in social science, finance, and I like this idea of data science genome. I'll just pitch this one thing. We are interested in basically building, in some sense, doing science of science. Let's say there is a new student. I see a lot of you with your eyes lit up many of these times. You're coming in and you're saying, hey, you know what, I want to learn what is new in neurosymbolic learning. And the system should not just do a Google search. It should give you a history. Hey, neurosymbolic system is first not new. Here is the initial work, but then it kind of is taken over by this group, and then now these are the most interesting directions. So in some sense, it's kind of like a genome that you can kind of look at and tell a story about this work. So we call it science of science, and we have a funded project on this where we are looking at it for one small problem. I'm looking at machine learning to see if we can build a interactive query tool that you can just put and say, I want to do this particular topic inside machine learning, and I pull everything that is relevant. But remember, the science is exploding, so even that would be a lot. So we are trying to figure out how to narrow that down. And of course, safety and ethics are extremely important. We need to understand the impact of what we do in terms of our science on the society. We cannot just say that it works for 99% of the population if we kill 1% of the population. So it's not correct. So we have to think about our ethics. And of course, finally, this is my real belief that if we do this right, we can teach the human 1 or 2 things. And I have some examples. I think I mentioned a couple of things in the workshop as well. So in one of the problems where we were predicting side effect of a drug, we thought the science said the side effect of the drug was heart attacks. But when we looked at the data deeper, we found that the side effect of the drug was actually an increased blood sugar level that caused the heart attack. And so I strongly believe if we do this right, that we can find some new diamonds every now and then, and actually potentially teach the human back as well. So with this, I'm stopping the presentation. This QR code will take you directly to our publications and project web page. Everything that I spoke now is publicly available for download. All the code is available for you to play with and ask. Feel free to email me. I'm happy to answer at any point. Okay. So with that, I'm ready to take questions, both here and in virtual. Could you turn on the mic, please? The mic.
Yeah. Any questions, students? Anybody on the online forum? They should be able to speak, right? Anyone on online? Any questions there?
He has a question here.
Oh,
No, he has a question right there.
oh sorry.
No, that's fine. Yeah.
So in human in loop, how do you account for errors, human-made errors?
Perfect question, right? That's where the data comes in. So as I said, right, even in the simple formulation of gradient boosting, you have I minus p, which comes from the data, and then I have the human constraint, and the human constraint could be definitely noisy as well. And remember, if I ask two experts, and I'm really saying this, two experts, they give you opposite views. Okay, all the way from masking, you get opposite views. So what we hope is that one of the data or the human advice should be correct for that combination. If both are wrong, there's nothing we can do. There's no free lunch, so we can't do anything. But we are hoping that when the human is wrong, the data is good. When the data is wrong, the human is good. And so that's the trade-off we are working with. Seems reasonable on many domains. It's very rare that both the data and there's a blind spot for both of them. And of course it can happen, particularly if you're predicting something like a rare disease, and the knowledge gets evolved. It's a hard problem. But yes, in general, we assume that the human is reasonably good. So that's why I said even in yesterday's workshop, I don't like the term crowd of experts. If you put a crowd together, it can never be experts. But I like to think of them as a set of experts, right? It's crowd's wisdom, yes, but not crowd of experts. So I like to think of it as, if there are a few experts who are good, who can provide the advice, then hopefully they are not bad at every point. Okay. Yeah.
Hey, am I audible?
Hello?
Yeah.
Yeah. So
Hey,
the prediction
Sriraam, great talk. I think there is one question.
Karthik, there is a question on here, so I will take that and then I'll come to you. Yeah.
Hi, sir. So that say the task is to predict whether a person has particular disease or not, then when the physician, when he provides the labels itself, there would be a trade-off between the precision and recall,
Sure.
which is in his mind itself. So is it okay to consider its label itself as an unbiased one, or we should consider that as unbiased?
So the label can be biased,
Yeah.
and that's where the advice comes in. So if the label is biased, but the advice is basically the rules that they give, we think that there are these important indicators, and as A increases, B increases, as blood sugar level increases, risk of heart attack increases, and so if you have those types of advice, this bias due to the label noise can be mitigated. And most of the time the advice is actually good because they are built on 50 years of their clinical literature or whatever, right? And so that those rules are really fantastic when we get them. Actually, in one of the problems that we worked with, gestational diabetes, the rules were so good, but the problem was the data was also so good. So we could have done one of the two. So there are problems like that where both of them are like gold. And so now we are taking these two and applying it on some rural gestational diabetes to see if we can boost their predictions. So your question is correct. The label noise, the label bias could come from any source, but that's where we are hoping that the knowledge will mitigate that. Okay, that's a good question. Thank you. Karthik, yes.
Hey, so there is a question in chat already, and I think I have to give a precedence to that, and then I'll ask my question. So the first question from chat is from Ravikant. He says, if there is misleading data, how can we avoid learning those data?
Yeah, so we can't explicitly avoid learning the data, but what we can do is figure out if the data is incorrect by applying the knowledge. So let's say that my data says that somebody has very high or very low blood sugar, very low everything, and then the data says that this person had a heart attack, a young person, right? Then we start asking the question, is the knowledge complete? And then maybe then the answer is that either the data is labeled incorrectly, or we have not collected the features that are important for predicting that particular aspect. So we can actually evaluate how good a data is by figuring out how well an example satisfies a constraint that the human provides or not. Okay, I hope I answered that question, and that's an explicit trade-off. If you write it out mathematically, you can think of it as just a linear combination: 1 minus lambda times something from the data plus lambda times something from the expert, and so you can basically figure out. So lambda is your hyperparameter. Okay, now everybody knows what that is. So lambda is your hyperparameter.
Sure.
Okay, Karthik, your question.
So no, there's one more question in chat, and after that, I'm going to ask my question. So, is this type of learning more computationally expensive?
That's an excellent question. That's an excellent question. Thank you. Turns out that if you have good advice, learning is actually very fast, because as I said, advice rules will replace the data. So I don't have to need the entire large data sets. I can actually learn from very small amount of data. But on the other hand, if the advice is not great, if the domain expert knowledge is not great, then it can be computationally expensive, because then I have to validate every example to make sure that your example satisfies some of these constraints. So the point I'm trying to make is that if you have access to good experts, then it's actually very fast. If your experts are very bad, then then they're not experts. But but that's what it is. That's what we get to work with.
So in fact, I think my question is quite related to that, right? So what if you don't have experts, but you have like smart undergrads, right? They are not like the experts in the field yet, but they have like fairly good knowledge, and they can probably contribute in useful ways. So and if you have like a lot of them, would this be could this be exploited in some fashion, where your confidence in every individual expert is a little low, but hoping that their collective expertise is sort of good or something like that?
Right. So it's like the wisdom of the crowd question. First is that if there are really smart undergrads, we want them in the group. Okay. So that's the first thing. So we really treat them as experts. So but to your point, I completely agree with you that there are cases where maybe one person doesn't know the exact answer to a question, but collectively they can come up with a good answer. And if we do have like that, then the extension of our method to do that is actually not that hard, because you can again if you can somehow put this in some form of a I don't know, I'm just making it's just an idea. One idea is kind of like an LD, a topic model type thing. If you can assign a hyperparameter weight to each of these people separately, then we can take some of their weighted average as a constraint and use that in the learned model. So the point is that there are ways that we can exploit this. Or my problem has always been that I work with one or two real experts, like as I said, physicians. That's where we work with. But how do we leverage a bunch of people? I think there's a lot of questions open on that problem. But I mean, it can be done by basically doing a weighted combination instead of. So it's a weighted combination, because there's already a linear combination. But inside the second term, you're going to have a weighted average instead of just a single statement. That's how I would do it.
Because in the real clinical setting also, you might have like a sort of inexperienced radiologist who's looking at some images and making some judgments, but can you still use their inputs? And I think,
Right.
okay, there's probably one more question here. Pranav asks, what is the nature of a typical expert advice? Is it like an additional label?
Right. So no, it's not just an additional label. It is actually some sort of a knowledge that talks about how a feature is related to a label. As I said, as a classic example, as BMI increases, the risk of diabetes increases. Okay. So that's not a label. That's basically collecting bunch of examples. For instance, even in elections, right, in the US, you can say things like, if you are in the Midwest, it is most likely going to vote Republican. The chances of being a Republican is higher. Now you can say in India, if you are in the northern part, at least in the last 10 years, the chances of voting BJP is higher. And you can just make that as a statement rather than as a label. And now what this gives you is actually, in some sense, it's a label. It's labeled over a bunch of examples than individual examples. I hope I answered your question, Pranav.
I think that's about it in the chat. Maybe you can go back to live questions. Thanks, Sriraam. Wonderful talk, very engaging as usual. We all enjoyed it.
Thank you, Karthik.
So
it's always a pleasure to come back and speak, and it's a major relief to do this in person after 2 years. I have no words to describe.
Absolutely.
It's good to see a live person in front of you.
Yeah, exactly. So yeah.
So very interesting talk. So I had like a very naive question. You were earlier talking about building several relational graphs,
Mhm.
each having a small amount of information or weight
Towards
And-
the
towards the overall goal. So if you look at clinical data
Mhm.
and especially at the data where like the events are like, as you said, high BMI increases heart rate, attack risk, and all those things. So if you look, so we are looking like, maybe we haven't talked in detail, but we are looking at preterm birth.
Mhm.
So we have around 1,300 different parameters. Not all of them are useful, right? Many are socioeconomic, so maybe we can ignore a large number of them, but there are several clinical parameters. So if you now start building each of these small relationships with the event being preterm or
birth.
normal term, can one use these small graphs to sort of build a sub-classification of what all a clinician should look for if a woman comes with these features?
Right.
What is the risk of
Yeah.
preterm?
That's a brilliant question. So first is we should talk because
Okay. Yeah.
I have a NIH grant
Okay.
on predicting preterm birth and gestational diabetes.
Oh, great.
So basically the whole class of adverse pregnancy outcomes
Yeah.
on women, right? So that's our grant, and we have done a lot of work in what you just, and it's in the 3rd year. So we've got some work done. So what these typically do when you do these graphs is that they identify groups of factors.
Yes.
So you just said socioeconomic. Actually, that is important because if they don't have access to good nutrition, there is a high chance that they are either developing gestational diabetes or they go for preterm birth.
Yeah.
Or most importantly, if they don't have access to, if they are not well taken care of, so if they have to work very hard physically,
Yeah.
then that also increases the chance of the
Especially
preterm birth.
rural women.
Right. So this is extremely important to look at. And what we can do with these smaller graphs, small relational trees that we talked about, is it starts building groups of these categories, which I tend to think of them as views. So they basically take, this is the socioeconomic view, this is the clinical view, this is the genetic view, this is their behavioral view. And so we have these different views that we can take and basically put them together to get this final prediction.
Okay.
So I think that's a great question. I think there's a lot of potential, and we should be working together.
We come to that. So one of the things that we have observed, like, so the data we have is all clinic. So it's basically ultrasound data and blood biochemistry and socioeconomic and anthropometric. We don't have genetic data because it's first is expensive, and then one of the ideas we had was that if you ask a pregnant woman here to go for a genetic testing, that raises a lot of flags
Yes.
for the family, and
Yes.
with all the issues with like female infanticide, it becomes a really, really big issue. So we are sort of cautious not to go
through the
beyond
sites.
the normal standard care a woman should get during pregnancy. So that's the point.
So we have a paper in JAMA that we have submitted to JAMA. So it's actually available in the PubMed, the Med archive, that where we are looking at genetic data on top of the data that you talked about.
Okay.
So we have sequenced about, I think, 3,000 women that we have data for. Not a lot, but it's still good enough. And there is a lot of the propensity score to, and we are looking at gestational diabetes. We are not looking at preterm birth yet, but there is a lot of genetic importance, right? If you have that score, then actually that gives you a good indicator. That's what we have figured out for this. So yeah, I mean, there is again some connections to that.
We can talk
Sure.
at length, but any further questions from here? Karthik, no other chat questions? Hello? I don't know whether you can hear me. Okay.
Okay.
Okay. Thanks, Sriraam.
Thank you.
Again for a wonderful talk. Really interesting sort of points for me to ponder over. So definitely
so much.
something that we can work on. And is Sridhar here? He's not here. Is he outside? Anything else? What's next? Do you know what's next? I have no. Hi, Ravi is here. Okay. Oh, just in time. You have any questions? No. All right. I was looking here. I mean, there's no mirror in front. Okay. No questions. Then thank you. Thank you, Sriraam, again for
Thanks
a
again.
wonderful talk.
Switch this.